Hi everybody, welcome to a recap of the last week in Stats 220 where we covered the module on probability, in particular random variables. So let's go through a few of the muddiest points this week. This post had to do with the binomial distributions, and it says in the quiz there were questions involving the binomial distribution and I didn't know how to solve it using the information from the modules. Instead, I used the binomial equation. So let's go through a binomial problem where we actually use the tables. 90% of Canadians have had chickenpox by the time they are adults. A random sample of 15 Canadian adults are selected. What is the probability that exactly 10 had chickenpox? Well, we can model this as a binomial distribution. So let x be the total number in the sample with chickenpox. Then x has a binomial distribution with n equal to 15 and p equal to 0.9. So we're assuming that each person, each of the 15 people, 1, 2, 3, 4, 15. This is person 1, 2, 3, 4, 15. Each of them acquires chickenpox independently, and each of them has a 90% probability that they will have had chickenpox by the time they're an adult, and a 10% chance that they didn't have chickenpox by the time they were an adult. So the probability that we're interested in is the probability that x is equal to 10. In other words, 10 of these people have had chickenpox and 5 don't. So how can we get that probability? We can go over here to the STA 220 page and go to probability distribution calculator and go over to the binomial table. And if we scroll down here to n is equal to 15, we're interested in the k, that k is equal to 10. But there is no p equal to 0.9 here. So what can we do? Well, 10 people having chickenpox by the time they're an adult means that 5 didn't get it. So this is the same as y is the total number in the sample without chickenpox. And that has a binomial distribution. Same n is equal to 15, but in this case, p is equal to 0.1, and we're interested in the probability that y is equal to 5. Now we can get that from the table, because that's over here. If we go down, if we look at n is equal to 15, k is equal to 5, and p is equal to 0.1, that probability is 0.0105. And so that's how you use the binomial table. This post for the muddiest point has to do with a question from the quiz involving the application of the rules for expected values and variances, and it has to do with the price of coffee and a muffin. So let's go through that. Sally gets a cup of coffee and a muffin every day for breakfast from one of the many coffee shops in her neighborhood. She picks a coffee shop each morning at random and independently of the previous day. The average price of a cup of coffee is $1.40 with a standard deviation of 30 cents. The average price of a muffin is $2.50 with a standard deviation of 15 cents, and the two prices are independent of each other. What is the mean and standard deviation of the amount that she spends on breakfast for the 2 days? Well, the price of her breakfast is the price of a coffee plus the price of a muffin. So that means that the expected value of breakfast is equal to the expected value of the coffee plus a muffin. And that's equal to the expected value of coffee plus the expected value of muffin, and we're given that that's equal to 1.40 plus 2.5, which is 3.9. The variance of one breakfast is equal to the variance of coffee plus a muffin. Now, using the rules for variances, since the price of coffee and muffin are independent of each other, that's just the variance of coffee plus the variance of a muffin. And in this case, that's equal to 0.3 squared, because we're given the standard deviations, plus 0.15 squared. And that's equal to 0.1125. Now we want the price of the expected value for 2 days. So the expected value for 2 days, the expected value of, let's say, breakfast 1 plus breakfast 2 is just the expected value of breakfast 1 plus the expected value of breakfast 2, and that's equal to 3.9 plus 3.9. The variance of breakfast 1 plus breakfast 2 is again equal to the sum of the variances, the variance of breakfast 1 plus the variance of breakfast 2. Variance of breakfast 1 plus the variance of breakfast 2. And in this case, that's equal to 0.1125 plus 0.1125. So for the standard deviation, that's equal to plus minus the square root of 2 times 0.1125. And that's how you use the rules for means and variances to figure out the standard deviation for her breakfast for 2 days. The next question is a normal distribution question and has to do with triathlons. So let's read the question. In triathlons, it's common for racers to be placed in age and gender groups. Friends Leo and Mary both completed the Hermosa Beach Triathlon, where Leo competed in the men's ages group, ages 30 to 34 group, while Mary competed in the women ages 25 to 29 group. Leo completed the race in 4,948 seconds, while Mary completed the race in 5,513 seconds. And then it gives you the different distributions of the finishing times in the age groups. And then the questions are, did Leo or Mary rank better in their respective groups, and what percent of triathletes did Leo finish faster than in his group? So to solve that problem, we know that Leo, the distribution in Leo's group is 4313 with a standard deviation of 583, and the distribution in Mary's group is normal with a mean of 5261 and a standard deviation 807. Their actual finishing times was 49:48, that's Leo, and Mary was 55:13, Mary's time. So how can we compare these two scores? Well, if we standardize and then look at the z-scores. So the z-score for Leo is 49:48 minus 43:13 divided by 583, which is 1.089. The z-score for Mary is 5513 minus 5261 divided by 807, which is 0.312. So we can picture this on a normal distribution, a normal with mean 0, standard deviation 1. So Leo's time is here over here, 1.089, and Mary's time is over here, 0.312. So who did better? Well, Mary did, because she has a smaller z-score. Smaller in this case is better. It means that you're faster. So Mary ranks better than Leo in their respective age groups. And in part B, it asks which percent of triathletes did Leo rank better than. Well, that's just the probability that Z is greater than 1.089. And to do this, we need to look at the normal table. So if we go over here, back to our probability distribution calculator, we can look at the normal table. And we want to look for 1.089. 1.09 is the closest, and that value is 0.8621. So this is 1 minus 0.8621, because what we're given on the normal table is we're given that 1.09, 1.09, we're given the area over here is 0.8621. Therefore, this is the area that we're interested in, and that has to be 1 minus 0.8621. Another way that we can calculate this probability is if we go back here and we look at the distributional calculator. We go to probability, choose normal, and then here in the value for x, enter 1.09. You'll see you get the same value, 0.8621, and that shows you again. This week, we're going to be watching videos about sampling distributions, and I look forward to seeing you online this week.